So I'm going to do a Blackboard talk. I'll try not to use too much the bottom of the board. Please do ask questions, because I know that there's a broad audience with computer scientists, physicists. I'll try to talk about a topic which is at the intersection between physics, computer science, and a bit of math. And it's a topic, so it's quantum LDPC code. So LDPC just means low density parity check. I will explain what it means. So basically, these are codes that are defined by sparse constraints. So this is something that you want in practice. And this is also some very natural mathematical object that you want to study. And I want to talk about these codes because they have been around for a long time, basically since the beginning of quantum computing. Kitaev toric code is an example of this. And for a long time, there was not much progress on these codes. So we knew about Kitaev toric code. I will talk about that. And they are good and interesting, but also not so good. And so for a long time, people wondered whether there could be good quantum LDPC codes in the sense that I will explain. And then, yeah, it took much effort to get there. And then suddenly, like 2 years ago, there was a breakthrough by Matt Hastings and colleagues that kind of pushed what we knew about these codes. And then suddenly, kind of all the problems were kind of solved. And now we know good quantum LDPC codes. So I'll try, probably it's a bit ambitious, but I will try in these 3 classes to tell you about these very good codes that we know exist now. And give you a flavor of what they are. The first paper about them was quite complicated. Now we have like some better constructions, which are easier. And so I'll try to explain this to you. That's the goal of the class. So first things first, so why do we care about quantum error correction, about quantum codes? Mostly for many people, it's really because we want to build a quantum computer, a fault-tolerant quantum computer. And the way we want to do that is by using quantum codes. So the main motivation is really fault-tolerant quantum computing. And the idea there is to really, so you want to compute, and everything is noisy in your machine. And so you want to protect information. And the way you will protect information is by encoding quantum information within a quantum code. So probably the most well-known example and what people are trying to do today is called the surface code. So it's a variation of Kitaev's original toric code. So it's like from the end of the 90s by Kitaev. And people are really trying to do that in the lab today, and they are doing it. There was an experiment. There was a paper about this last week by the Google group. So basically, the idea is that you will encode a single logical qubit in an array of many physical qubits. So basically, what you take a grid of square root n times square root n physical qubits, and somehow within that grid, you can encode one logical qubit. So I will explain, maybe not now, but I will explain how you do that. And basically, there are kind of 2 interesting things in these constructions, is that everything is local. So you can think of, if you want the qubits, they sit on points in this grid. And so everything is local. So every qubit has to talk only to its neighbors. And everything is in 2D. So you really have like 2 nice things. So you have a 2D, 2-dimensional local code. And so people are trying to do that now. And so last week there was this paper by the Google group, and they did 2 things. They did a grid of 5 by 5, and they did a grid 7 by 7. And what they showed in their experiment is that if you take a grid 7 by 7, some of the qubit that you encode, that you protect like this, is better than the qubit that you have if you do 5 by 5. And in theory, as you increase n, you should get better and better protection. But okay, so that's the surface code. So is it very good or not? Well, so what I'm saying is that you encode 1 qubit within this set of n physical qubits. So you have seen probably yesterday in the talks of Victor Albert, this notation KN, NKD. So just meaning that you have a code with n physical qubits, you encode k logical qubits, you protect k qubits, and the distance of the code is the, the minimum size of an error that you cannot correct. So ideally, you want these two numbers to be as large as possible. If you have a given n, you want to encode as many qubits as you can, and you want the best distance as you can to get better protection. So what are these parameters for this surface code? Well, they're not that good. So if you have a grid of square root n by square root n, you have n qubits, n physical qubits. So I said you encode only one logical qubit. Okay, so k is 1. And what is the distance of this thing is square root n. And in particular, it turns out that, if you have an error that corresponds to somehow like a line like this that crosses the surface, then you get an error that you cannot correct. So it's not that good, no? It's just one qubit and one logical qubit, and the distance is square root n. Can you do better than that? So in theory, you could hope to get both k and d to be linear in n. Okay, there's nothing that a priori prevents that. So can we do that? Well, it turns out that if you really want to stick to these constraints, that you have something 2D and that you have something local, so 2D means that all the qubits are in this 2D plane, and local means that you only have nearest neighbors interaction in 2D. Then it turns out that the KTF code, the surface code, is pretty much optimal. Okay, so there's a trade-off. You can increase a little bit the number of logical qubits, but when you do that, you decrease the distance. And basically, the trade-off that you get here is optimal. You cannot do much better than that. So if you want to improve this, you have to drop one of these two things. And the things we want to drop is the 2D part. Okay, we want something local, so we want to keep something that is local, so that is defined by sparse parity checks. But maybe, okay, we say, okay, we don't want, okay, to restrict ourselves to interactions that only involve, nearest neighbors interactions. You say, okay, so right now, today, people in the lab, they really like this. Okay, they really want to put, superconducting qubits everywhere, and they want to talk to the neighbors. But you say, okay, in 20 years, in 30 years, maybe we'll have different technologies, not working with superconducting qubits, but with something else, where it will be easy to do, a get between this qubit and that qubit. Okay, so what we want is we want something local, so we want each qubit to only talk to a constant number of other qubits. But maybe we want to, relax the assumption of 2D. Okay, and if we do that, so what we get is by definition a quantum LDPC code. We keep the locality part. So we keep that each qubit only talks to a constant number of qubits, but we drop this thing. And in that case, the hope is to get much better parameters than this. Okay, and yeah, well, it was not so easy, so people have looked at that for a while. So in 2009, there was a construction by Jean-Pierre Tillich and Gilles Zemmour that improved this thing. And they showed that you could do better than the surface code, so you could have n qubits, a number of logical qubits that was scaling linearly with n, so something scaling like linearly with n, and the distance was still square root n, or constant and square root n. Okay, so that was like 15 years ago, so people realized that you could increase the dimension of your code like this. And then for more than 10 years, people have tried to improve this bound on the distance. This was really like a mystery, whether these quantum LDPC codes, they could have a distance that was better than square root n. And I would say that 2 or 3 years ago, if you had sampled like a group of experts in this field, and you have asked them whether it was possible or not that better codes exist, I would have said that, yeah, please.
I don't know, there's also a question in this one.
Yeah.
But I will ask.
Yeah, please.
Just a small one. These codes have that associated with them, or does that like DB or something?
Like what?
The dimension of the surface.
No. Yeah. So here already, It's not in 2D. It's not in 3D. It's like you cannot embed them.
But was that a constant dimension in n, or was it not constant?
No, it's not constant, the dimension in general. Yes?
So, physicists, I mean, assume some error model, I don't know, locally, or something, and physicists would say, oh, presumably this has an error threshold already.
Yes, and they do.
So what's the point of going from square root n to this?
Yes, because we're scientists and we want to know the truth, you know? So yeah, no, you're right. You're perfectly right. So what I've been shown is that these codes, yeah, they have a threshold. And these codes, they are enough if you want to do fault-tolerant quantum computing with constant overhead. So there was a paper by Gottesman like 10 years ago that was showing that if you had good quantum LDPC codes with some good properties, good decoding algorithm, then you could do much better than the concatenated schemes that we had. And these codes, they do that. So these codes already, they kind of give you the right tools if you want to do fault-tolerant quantum computing and fight errors in a random, not adversarial model. So if you have really random errors, these codes, they're good enough. But still it's a mystery. Can we beat this bound, this square root n bound? But yeah, I agree. It's like more for the game. It's a game to understand whether it's possible or not. There was a question there? It's good.
So when people say that it's of order n, are there estimates on the constant? If you give, I don't know, 0.00?
This one? Yeah, the rate. So the dimension here, you can put whatever you want. So you can just choose it as you want.
No, the question is about the constant.
The big O constant.
The big O constant, is it 0.11000 or what?
So no. So for this thing, so here you put it's any value that you want. So you can get 0.9 times n if you want. So here the dimension you can just fix it as you want. But then as you fix it, of course, the distance it will suffer. If you increase the dimension too much, the distance will suffer. So you have a trade-off for the constants. But you can take any constant in front of n. Yeah. Okay, and then, so for then more than 10 years, nobody made any progress on this question, and it was really not clear. I mean, all the constructions that people could think of, they were always hitting this bound of the square root n bound on distance. And okay, so can we do better than this? Okay, so the answer is yes. So 2 years ago, there was like a breakthrough. So first there was a breakthrough by Hastings and co-authors that went from square root n to the 0.6. And then, 18 months ago, Potev and Kelechev showed that we could do like good quantum LDPC code. So good means that everything is linear in n. So the dimension and the distance are both linear in n. And their initial construction was not too easy. We'll talk about a different construction that we have with one co-author that is a bit easier. Okay, and that's the goal of this class, to kind of present to you these constructions. But because they are not so easy, the first thing I want to do is really to look at the classical case first. So today I will talk mostly about classical codes. Yes?
I disagree with some computer science. If you have a linear distance, that means you can store information efficiently, package efficiently in space. And sorry, if you have linear rate.
Yes?
More efficiently, if you have linear distance, you have a better threshold, higher threshold.
Yeah, no, that's true. Yes.
So thresholds have not been studied.
No, not yet. No, yeah, so in principle, the better code that you have, the better you expect it to perform. So yeah, so we expect that if we have linear distance, it will be better than square root distance. Yes?
In the new code, is there still a relation between K and E where K...
Yeah, always, but now it will just, but at the level of constants. But this is not yet understood at this point. So right now the construction that we have is really asymptotic. It's really for very big n, and we have bounds for this quantity, but they're not tight yet for the distance. We know it scales linearly with n. We have lower bounds, upper bounds, but there's still a gap. We don't know exactly what is the distance. this code. Yes.
So clearly the interesting thing is the ratio between K and N, but is there any significance of each one of them? I can code like 5 or 50 in 100. What would be the difference?
Yeah, so, yes. Well, usually it's because of this trade-off. So when you increase N, so what will happen is that, you keep the rate constant. So K over N will be constant, and when you increase N with a fixed rate, the distance will tend to grow. So the larger the N, the better the distance. Yes?
The rate between K and N is the property of the code, and it's something that you can use.
Well, it's a thing. So depending on the construction. So for some constructions, if you have the surface code, K over N is just 1 over N. You have 1 qubit in this thing. But with the more recent constructions, they are more tunable. So you can somehow, you have like a large family of codes, and you can fix the rate as you want.
Can you change the distance?
Sorry?
So you can change the distance?
Yes. Yes. Okay, so just to... So as I said, today I want to talk mostly about the classical part. So in the classical world, kind of the simplest code that you can think of is a repetition code. Okay, so you encode 1 bit into n bits, and you just say, okay, you just repeat the bit n times. Okay, that's the repetition code. It's very kind of trivial code. You encode 1 bit into n bits, and the distance is n. So the distance is really good, okay, because you have only one non-trivial code word, which is the all one code word. And so in the quantum world, the kind of the equivalent or the version of the repetition code is really the surface code. So the guy that plays the role somehow of the repetition code, when you generalize the repetition code, you really, in a natural way, you get to the surface code. So that's kind of the easy thing. And now we want to have good codes. So we want K and D to both scale linearly with N. So in the classical world, we know how to do that. So we have good LDPC. And the good LDPC codes that we have, they're called expander codes. Or at least that's one family of good LDPC codes, expander codes. So they were devised by Sipser and Spielmann, like around 96. And they're really, really good. It was kind of a surprise when these codes appeared. So they are explicit codes, which are good, and they come with an efficient decoding algorithm. Yes?
N over 2 to the distance in classical.
So the N over 2 would be the number of errors that you can correct. So the distance is really the distance of a code is the minimum weight of a code word which is different from 0. So the minimum weight of X with X in a code, but different from 0. Okay, so for the repetition code, you have only 2 code words. You have the all 0 code word and the all 1 code word. So the distance is N. But you're right, the number of errors that you can tolerate is N over 2. Okay, if you corrupt, but the two quantities are related by factor 2, basically. And somehow the good quantum LDPC codes that are here, they're really the generalization of these guys. So before I can explain to you this construction, I need to spend a little time to talk to you about classical expander codes. Okay, so that's the plan for today, to explain these things. And then tomorrow, we'll go to the quantum part and look at those.
Just one more question.
Yes.
If I change, the distance when I increase the rate, so also in the photography code, I can decide to have a constant distance and just increase the number of qubits and punch forward.
Yes.
And increase the number of logical qubits, and you have the same distance. So what's really
So no, yeah. So here you can, as you said, you can punch holes. But if you do that, So you can get to some k, and then the distance that you get will be, I guess it's square root n, maybe over k. Yes. So, so the point is that here, if you look at the product of k times d for the toric code and for any 2D local code, this thing is order n at most. Order, square root n. Yeah, square root n. I think it should be, it should be this. K d squared is order of n. So yeah, so you can increase k, but you decrease d. The point of these new codes is that you can have k d squared order of n cubed. So you have both k and d linear in n. So here, yeah, it's true. You can make holes, or you can divide your physical qubits in many patches of small surface codes. But all these tricks, they will never give you this kind of scaling. Yeah, so what I want to talk today now is about the classical case, so classical LDPC codes. So these guys, they were discovered quite early by Gallagher in his thesis, like in the 60s. So what is a classical LDPC code? So it's a classical code, so it's a linear subspace of F2 to the n. And it's just defined as a kernel of some, what is called a parity check matrix, H, which is sparse. So H is just a 0-1 matrix. Like this. And the code space is any vector which is in the kernel of this thing. Okay, so all the set of x of length n such that hx equals 0. Okay, and the matrix is sparse, so the matrix has size. So you have n columns, and you have typically n minus k rows. So each row gives you an equation that you have to satisfy, so it gives you a constraint. And so the dimension typically of this thing is if the constraints are independent, will be n minus the number of equations, so k.
FKN.
Sorry?
Yes, explain this notation.
F2, so it's just F2 to the n, so it's bit strings, okay, of length n. Okay, and the matrix is sparse, just means that you have a constant number of ones per row and per column. So you can think, so for instance, typically people can use this. They use, matrices with 6 ones per row and 3 ones per column. And what Gallagher found, like in the 60s, is that if you take a random parity check matrix, which is sparse like this, so you just pick it at random, so there are efficient algorithms to do that. Then with high probability, so for a random matrix, sparse matrix, so with high probability, you get a good code. So you get, so K, if you want to have K linear in n, it's easy. You just take like a rectangular matrix. You just want to take the number of rows that scales with n, but that is, with the constant that you want. So you can fix the dimension as you want. And then with high probability, you can show that the distance will be also linear in n. So okay, so if you just take a random classical LDPC code, you know that it's good with high probability. And then, okay, so these codes, they came with good decoders that Gallagher figured out, like in the 60s, and then they were forgotten, because at that time, we didn't have like good computers to really implement these things. So they were forgotten for 30 years, and then in the 90s, they were discovered again. And now people really use those codes, and these codes, they are used in Wi-Fi, in 5G, and people really love these classical LDPC codes.
So what's sparse?
So sparse just means that this matrix, the number of ones per row and per column is a constant, independent of n. So sparse means number of ones per row or column is order 1. Okay, so it's a constant. So it can be 6.
Decoding, you really use them?
So people use them, I think, yeah, I don't know, and between a few thousands and a few millions. Yeah, I think so. Yeah, because, yeah.
One is to do with billion, with very sparse.
Yes. Yeah, so these things are really, really sparse, yes.
And this can detect errors at the distance of billion.
They will detect errors like on the constant fractions of the bits, yes.
And they based on the parity check.
And the detection, everything is based on the parity checks, yes.
How do you code the specific string of bits in this question?
Okay, so that's a good question. So this is so when you have a code, so there are kind of two ways to define a classical code. You can define it as a kernel of some matrix, because it's a linear subspace, or you can also define it as the image of some matrix. Okay, so you should find, so you need to find what is called the generator matrix, generating matrix of the code. Usually it's called G, and the code, so it's really the image of G. Okay, so G is just a matrix such that G H transpose equals 0. Okay, so if you, so you need to solve like a linear system. So you find this matrix G, and then for any vector that you want to encode, you just apply G to the vector, and it gives you a code
I
word.
think a simple example would help some people. Oh, it's too much to ask.
Yeah. I don't know.
Why is it important for a classical code to be sparse?
Okay. So why is it good to be sparse? One good reason is for decoding, okay? Because, you know, when you want to decode what you get, so usually, so what you do, you encode, so in the classical setting, codes are used for communication, okay? So someone wants to communicate with someone else, you want to send information on a classical channel. So what you do is you have Alice, she picks a code word in C, and she sends it to Bob, and Bob receives, you know, a noisy version of X. So he receives Y equal X plus E, where E is a binary error. So what does he do? So he wants to recover X. So what he can do is what is called computing the syndrome of Y. So the syndrome is just defined as H times Y. Okay, you have the parity check matrix that everybody knows, and you just compute this thing. And you check, so basically you check whether Y satisfies all these equations or not. Okay, so this is a bit string. So this is a bit strings of length n minus k. You have n minus k parity checks. And turns out that this thing is also equal, you know, everything is linear. So it's hx plus he. So hx equals 0 because you have a code word. So this is just he. And basically the decoding problem is given this string, he, okay, recover e. Recover e. So in general, this looks easy. It's just, you know, a linear inversion. You have like a linear set of equations. But the tricky part is that there are many solutions to this. Because, you know, if you have any solution for that, then if you add a code word, you will also get a solution for that. So what you want, in addition, is you want to find the E of smallest weight that satisfies this thing. Okay, and now this becomes a much harder problem. Okay, so this is an NP hard problem in general. If you're given some matrix H without any specific structure and some E, and you want to recover the E of smallest weight that satisfies this thing, this is NP hard. And so people, they want to design, you know, efficient decoding algorithms. So that you want to find codes, class of codes, for which these problems becomes easy. And when the matrix is sparse, you can have like a graph representation of the code. Okay, that makes everything easy. So what you can do, you put your n bits as a set of vertices. You put the n minus k equations as a different set of vertices, and then you put every time you have an equation, it gives you, you know, So this equation involves this bit, and that bit. And okay, you do it like this. And now, because this matrix is sparse, the degree of this thing is constant. So you have a sparse graph. You have a sparse graph, and you can use that sparse graph to do, efficient decoding algorithms. So you can really do efficient decoding because of this sparsity. And the sparsity really helps you. Okay. Okay, so in the classical case, we know that if we take random codes, random LDPC codes, they will be good with high probability. Yes?
So for encoding, you multiply by
Yes, yes. So if you have message M, which is like a k-bit message, then the encoding of M is just G applied to M. Okay, so G is a matrix of size n minus, n times k.
In your choose the instance, you pass to this spouse in order to see a computation will be efficiency, but those spouse steps have to do with the encoding itself. If you have strong enough message which is not spouse.
So, yeah, so in some cases, you can use H, which is not sparse, if you have enough structure. So H needs to be structured. If you have no structure for H, and if it's not sparse, then it's believed to be very hard to solve. And actually, right now you have all this post-quantum cryptography.
So the problem is the solving of the equation of the coding itself. If I have computers which use H, which is not sparse.
Yeah, if you have if you have exponential time, you can, then yes.
If you think about that, for a general H matrix, it would be just an integer linear.
Yes. Okay, so in the classical case, if we take a random code, it's good with high probability, but people really cared about, finding explicit examples. So explicit families of good codes. And what I want to mention is a very useful kind of idea to construct explicit codes. So it's called the Tanner code construction. So it's due to Tanner in 81. So the idea is to define a classical code, a large one, from a large graph and a small code. Okay, so you have like a small code plus large graph. And it gives you a large code. So how do you do that? The idea is that we'll take some graph. So with a set of vertices, so I will take for simplicity, I will take a bipartite graph. So with two sets of vertices, A and B, and some edges. Okay, so I have some set A of vertices, I have some set B of vertices. I will always take the size of A to be equal to the size of B equal n. So you have 2n vertices. And now you have edges in my graph. And what I will do, so how do I define a classical code out of this? What I will do is I will put the bits of the code on the edges. Okay, so my code words, they will be like bit strings with the bits labeled by edges. Okay, so 0, 1 to the E. So really, a code word will be like zeros and ones for each edge. And then, so these are the bits. I need to define some constraints, linear constraints to get a classical code. So what I will do, I will take a graph which is delta regular. So meaning that the degree of all my vertices, so the number of edges incident to every vertex is the same everywhere, so it will be of size delta. Okay, that will be like, in some cases, a constant independent of n, not always. And so how do I impose linearity constraints? What I will do is So, so for every vertex in its neighborhood, it has a set of delta edges. And if you label them, so you can see these delta edges as a, it's just F2 to the delta. You have a set of length delta. So what you can do, you can take a small code of length delta. So C0, which has, so it's a small code on delta bits with some dimension k, which is just rho times delta for some rho and some distance. And what you will ask for the code words of your code is that for every vertex, what you want is that if you look at the restriction of x around this vertex, so if you have some vertex v, so you can look at x sub v, so this would be just the restriction of x to the edges incident to v. What you want is that this thing belongs to the small code. Okay, does that make sense? So the Tanner code construction, so it gives you a classical code out of a graph and a small code. So it's a set of all the vectors in 0, 1 to the e, such that for every vertex, if you look at the neighborhood, so if you look at the subvector of x for the coordinates incident to the vertex v, this should belong to the small code for all vertex.
So for every edge, there's a bit, right?
So for every edge, there's a bit.
And then you find the neighbor of the adjacent edges of that edge.
So you define, so for every edge, there's a bit. So you define the neighborhood of a vertex. Okay. So for every vertex is incident to delta edges, delta bits. So you can just look at the restriction of x. So x is just the assignment of bits everywhere on the edges. So just look at x sub v. So this would be just these guys, the value of this one, and that one. Okay, so this thing is a vector of length delta, because the degree of this graph is delta. And what I ask is that this vector of length delta belongs to some small code.
How many code words are there?
Right. So good question. So how many? So how big is the code? So in general, we don't quite know. It will depend really on how you assign. You need to label your edges somehow. But what you can do to get a lower bound on the dimension is just to count the number of constraints, of parity checks that you have. Okay, so the number of bits is what? So it's the number of edges, so it's delta times n. Okay, the number of edges, you have n vertices on the right, on the left, and each of them is incident to delta edges. You have n times delta bits. The number of constraints, what is it? So it's the number of vertices. So for each vertex, you have a set of constraints. So it's the number of vertices. The number of vertices is 2n. Okay, you have n on the left, n on the right. And then how many constraints do you have at each vertex? So at each vertex, you have a code of rate rho. So the dimension of this code is rho times delta. So the number of independent equations for C0 is, so the number of equations is 1 minus rho times delta. Okay, so you have delta bits, rho times delta encoded bits if you want. So the number of equations is just the difference between these two things. So for every vertex, you have, at most, you have this number of equations, 1 minus rho delta. So n minus k, so the number of constraints that you have in your Tanner code, okay, for the Tanner code is what? Okay, so maybe not, or the rate if you want, the rate of the Tanner code. So it's the number of encoded bits over the number of edges. So what is it? It's 1 minus the number of constraints divided by the number of bits. So it's 1 minus this divided by that. So it's 1 minus 2, 1 minus rho. So it's 2 rho minus 1. At least because here I just counted how many equations I have, but maybe some equations are redundant. Maybe they're not all independent, but the number of equations is at most this. So the rate of the code is at least this thing. In particular, so you see that it will be positive if rho is at least 1/2. So what you want is that you want each of these small codes to have like a large rate. Okay, if you put too many constraints on each of these small codes, then you will not get anything at the end. But if you put rho large enough, greater than 1/2, then you get a positive rate.
They exist, small codes with large rho?
Yeah. So for any, yes, because a code is just a linear subspace. So you can put the dimension that you want for your linear subspace. So if you have a code C0, it's just the kernel of some matrix. So if you take it square, the matrix, then the kernel will typically have dimension 0. But if you take it, rectangular but very thin, it will have like a large dimension.
But you mentioned a trade-off between making rho large and making S. Then S will be too small.
Delta. Yeah. But no, in general. So in the classical case, so these two things, rho and delta, they can both be constants, and we know the optimal trade-off that they can achieve. Yeah, so I want to illustrate this with two families of Tanner codes. So one will be the expander codes I was mentioning at the beginning. So this will be the second family. And the first family I want to mention is called product codes. Because I will need those two things for the quantum case. So one example is product codes. So as I said, I need a graph and I need small code. So the graph that I can take, the kind of a natural one, is the complete bipartite graph. So my graph will be KNN, so it's the complete bipartite graph. So meaning that for every just as before, you have two sets of vertices, A and B, both of size n, and then I put every possible edge between these guys. Okay, so if I do that, then if I have a vertex A on the left, a vertex B on the right, then the edge that connects these two things is uniquely defined. It's by A, B. Okay, so there's a way to label the edges. All the edges, they will be labeled by an element of A and an element of B. So somehow, the edges, if you want to assign bit values to every edge, the way you can do that is by representing your vector X as a matrix, where the rows are indexed by A and the columns are indexed by B. Okay, and then you have some A, B. Okay, so X will be a set of zeros and ones, and every coordinate of X will be an entry in a matrix like this. And then, so if I generalize a little bit the construction that I had before, so I take two different codes. So on the right, sorry, on the left, the local code, I will call them CB, and the local codes on the left, I will call them CA. And then what happens if I ask, say that for every vertex B on the left, the set of, if I look at the restriction of the code word and the edges incident to B, I ask this to be a code word of CA. So the set of edges that leave B, they are here. So if B is here, so these are these guys, this part of the matrix. And what I ask is that this column should be a code word of CA. Okay? So basically what I'm asking is that for X will belong to this product code, so this will be denoted CA times CB. So X belongs to CA times CB if for every column of X of this matrix, I have a code word of CA. And for every row of this matrix, so for any A, so for every row indexed by some A, I have a code word of CB. Okay, so that's called the product code, CA times CB. So it's just, so the code words, they're represented by matrices, and I ask that every column belongs to CA, to some small code, and every row belongs to CB. So how do I do that? How do I encode in this thing? So you can write it explicit. So what you can do, if you want, so okay, so what, before I tell you how I do that, so what are the parameters of this code? So this code has length n squared. Okay, you have n squared entries in this matrix. So if I have, okay, so CA, I assume that it's like a code of length n with KA bits and distance dA, and same for CB. So it's n KB dB. Then you can show that the length of this thing is n squared. The dimension is just the product of the dimensions. And the distance is the product of the distances. So it's really good. This thing is, and in particular, what is nice is that the dimension, you see that if both dimensions of the component codes are non-zero, then the dimension of this thing is non-zero. So somehow it's much better than the bond that we had before. So the bond that we had before on the dimension set was saying that if the rates of these two codes of the local code is at least 1/2, then the rate of the final code is positive. But here for this specific construction, as soon as both rates are non-zero, I get something which is non-zero. And this thing is really because I have a smart labeling of the edges around every vertex. And I can see everything like with this matrix thing. So maybe I can explain offline how I can do that, or I can encode in this thing.
Can I do it again after I square the size of the code?
Yes, so you can do this. Yeah. So you can do C1 times C2 times C whatever P, and it will be some code of length n to the P and typically K to the P. Yeah, it's perfect, this thing. 3 more minutes just to say, because, okay, so that's the product code. I didn't get to where I wanted to go, which are expander codes, classical expander codes, which are because, so here I kind of cheated a little bit. Somehow I want to, okay, so it's true that I define a large code out of 2 smallish codes, but they're not that small, okay? So each of the components, so if I want like a code of length n at the end, the component code have to be like size square root n each. So if both of these things are good, then the thing here will be good. But what I really want is to have something sparse. So what I kind of want is, I want to replace this graph, this complete graph, by something which is sparse. So I want much fewer edges in this thing to get something like a better construction. But when I do that, I don't want to lose the properties of this nice graph. So this complete bipartite graph is quite nice. It's it's complete. So if you remove like a few set of edges, it will not be disconnected. You have good expansion properties. So I want somehow like a sparse approximation of that graph if I want to get better classical LDPC codes. And the way I do that is by taking something called expander graph. So what I want is to replace this full, complete bipartite graph by an expander graph. I will not define in detail what this means, but basically what the main property I need from this is that it behaves in kind of in the same way as this one. So in which sense? So what is the property that I want? So again, I have like this bipartite graph AB. And the property that I want is that if I take any two subsets, S of A and T of B, the property that I need is that somehow if I just want to count the number of, so I have edges all over the place, but now if I just restrict to the edges that go from an element of S to an element of T, I want this set to behave kind of in a random way. So in which sense? In the sense that if I count the number of edges between S and T, where it should behave as if this thing was random for all S and T. So what should this be? So if I had something completely random, what would be the expected value of this thing? So what's the expected value of edges that go from S to T? So what I do is I start with any point in S, and basically I just want to see what is the expected value of how many edges will land in T. So I start with any point in S, and what's the probability of getting in T? So you have delta edges. So I will take something which is delta regular. So you have delta edges out of every vertex. So for every edge, so you have delta edges. And what is the probability that a random edge falls into T? Well, it's basically size of T over N. Okay, so that's the kind of, the expected value is this of the number of edges. And what I want is that somehow this expected value is not too far off. So I will allow something, an error term, which is, so usually when you have something called an lambda expander, it means that this thing, you have a bound that holds like this, but you have to add this error term, which is lambda times square root of S times T. Okay, and what is the value of lambda that you can achieve in practice? So lambda, you can take, if you have a really good expander, you can take 2 square root delta. Okay, so that's the property that I kind of want. So, yes. Yes, independent of n. So that's the only property that I will want. So I tell you that these things exist. We know how to build these things, to construct these things explicitly. So there are graphs called lambda expander graphs, for which every time you take any S and any T like this subsets, the number of edges between S and T will be this thing. And we will work in a regime where actually this number is smaller than the second one. The second one will be the larger one. Okay, and so the main idea of Sipser and Spielmann expander codes was to do the Tanner code construction on this kind of graph. So you have an expander graph, and you put like a local code C0 as before. So the C0 is just as before, delta, rho delta, and some delta times delta. And if you do that, then the magic happens. This thing has distance linear in n. And the proof is not very complicated. I will not do it in detail, but basically, the thing is that, so if you look at the code word of this thing, so it's an X, okay, you look at the X in this Tanner, this expander code. So it's a set of edges. So this set of edges defines two sets, S and T, so the vertices that are adjacent to X. And then what happens is that because it is a Tanner code, so for every every vertex in S or T, the number of edges that go to the other one is at least delta times delta, because locally you have a code word of the small code. Okay, so the degree, both in S and in T, the average degree of the subgraph induced by X is at least delta, small delta times the degree. And if you just plug this, so this means that if you look at the number of edges between S and T, so it is, by definition, so it is ds. So it's both ds times S and dt, the average degree times T. So it's also equal to 1. So it's the geometric mean of these two things. And now if you just, look at this equation, so you can divide everything by square root st, so what you get is, and ds and dt, they are at least delta times delta. So if you divide everything by square root st, what you get, and you move things the other way, so what you get is you get square root st times delta n, which is at least delta delta minus this lambda, which is 2 square root delta. So square root of st is at least n over delta times this quantity. So both S and T have size at least linear in n. So the weight of X, so if you take any non-zero code word in this Tanner code, you have that the weight of X is at least some constant times n. Okay, and this proves that these codes are good. Yes, I will stop there because, sorry, I was a bit slow. Any question? Yes.
Say again, where does the lambda theorem come from?
I didn't explain where it comes from. I'm just saying that there are different ways to, so there's this notion of expansion, exponent graphs. So usually the way it's defined, you look at the adjacency matrix of the graph, and you look at the second largest eigenvalue, and it's called delta. And if you have a graph such that the second eigenvalue of the adjacency matrix is delta, then you can show these kind of things. You can show that the number of edges between any two sets is bounded like this. And the best value that you can take for delta is roughly square root delta, square root of the decay.
Is there a simple intuition or reason why do I want to expect the value of number of edges from S to P to be like a random choice?
Yeah, these things, so these exponent graphs, these are like kind of combinatorial objects. So they can be studied with the tools of, random walks and things like this. So what people care about is, they have a graph and you want to find a graph where if you do a random walk on that graph, very quickly you will get like at a very, very random place in the graph. So if you have a complete graph, complete bipartite graph, this will happen. And then what people cared about is to have approximations of this kind of graphs, but with sparse graphs.
So is it because random graph?
Yeah, so a random sparse graph is an expander with high probability. But then the big question, like LDPC codes, but then the big question was to find explicit expander graphs. And
Can you go the SDPC again, quickly?
Yeah, so ds and dt, they're just the average degree of a vertex in S or in T when you only look at the subgraph where you only keep the edges between S and T.